I say put Eddie in charge.
Would I make as much as I would at Buc-ee's?
The crazy salaries
And
that they
saw
pay
how
at
much
Buc-ee's.
money I could make working at Buc-ee's.
What is it? What?
She could double her pay if she became a Buc-ee's manager.
No. Wait.
Nobody get any ideas here.
How much do they make? No. I need to.
I know,
I
we're
need
in a
to
wrong
send that
profession,
to
y'all.
You need to
Diego.
reprioritize your whole
He loves Buc-ee's.
existence.
There you go.
What? That doesn't make any sense. Assistant general manager?
Assistant to the general manager.
Car wash manager?
Right?
What is the car wash manager?
A car wash manager.
125,000
Car
plus.
wash manager.
I
makes
can
twice
wash a
what
car
I
for
make.
Manage a
$125,000.
lot of car washes for that kind of money.
Yeah.
Welcome to Walkabout the Galaxy, the quirky astronomy podcast where the science is universal, the opinions are personal, and the trivia is nerdy. We are strange, charm, top and down. The astroquarks, also known as Josh Caldwell.
Addie Dove.
Jim Cooney.
And Audrey Martin.
Coming to you from the Walkabout studio at the University of Central Florida. Remember our listener challenge to come up with a cool name for the particle that is formed by combining one each of a strange, charm, top and down quark.
Right.
Tetraquark is not an acceptable submission for this listener challenge. Remember to subscribe to us on all platforms, including YouTube, Facebook, Twitter, and Instagram, but not Quackster, Moodle.com, or cockadoodledoo.com.
Moodle with an M?
With an M. Moodle.com. Quackster, or cockadoodledoo.com.
One of those is real?
One of those is real.
They're
Moodle.
all
Moodle.
are porn sites. But yeah, Moodle.
Moodle?
You're both going Moodle?
I think,
Yeah.
what is it, Quackster?
Quackster.
I want there to be a website about ducks called Quackster.
Quackster.
Yeah.
Yeah.
People who love ducks, they get together and talk about ducks.
Yeah.
Sadly, there is not.
No! I'm going to start
It
it.
could be. Yeah.
But maybe you can create it.
It could also be
Sweet,
for crazy
that's good
people.
news.
Yeah. No, it's Moodle.
Win-win for me.
It
It is Moodle.
It's Moodle.
Hurry
You
it
guys
up.
got
Is it for
this one.
cows?
It is not.
It's you just post what your mood is. It's just
It's
you
not
just post
that
an
either.
emoji
Like
for
a
your
mood
mood.
ring.
It's not
It's
that
a
either.
moodle doodle. You do a little doodle of your mood. That's what it is.
I looked it up and I forgot what it is. But it inspired.
Well, then there we go.
I went with Moo to make Quackster and Cockadoodledoo.
Yeah, I figured.
But I had to be careful and actually make sure that there wasn't a Quackster.
Riley would be
or
really
a
excited about this conversation.
or a cockadoodledoo.com because there are a lot of crazy websites out there.
Yeah.
You can contact us anytime at wtg@ucf.edu with questions, compliments, and to find out how to get a cool Walkabout t-shirt, which I forgot to put on.
He's not wearing any shirt.
Or any... Or a Walkabout t-shirt that I didn't forget
You're
to
wearing
put
a
on
lovely...
because it's a brand new t-shirt.
Yeah, you would get your own t-shirt. Unless,
t-shirt.
by special request, you probably could get a Josh Warren t-shirt.
If you want me to
you
put
really
the
want
t-shirt
that.
on before I send it to you,
Weird.
that's a little bit weird, but I will do it.
Pre or post run.
Ew. Gross.
Yeah.
So we can take with questions, compliments, and odd t-shirt requests.
People
to
request that all the time on Quackadoodle.
Cockadoodle.
I mixed them. I made a new
Made a
one.
new one. Our stumper today is nomenclatural. Planetary scientists, as we know,
That's us.
like to name
We know
things after
People like to
People-
name things, man.
they do.
I love naming things.
Yeah.
So we have, asteroid Addie Dove, asteroid Josh Caldwell, the Grand Canyon. These are like some of the
Those are names of things.
Big ones.
Those are proper
The
nouns.
big ones people talk about.
these are the notable features in the solar system. The Amazon River,
Sure.
right?
Yeah. The Nile.
Asteroid 29602 Joshua Caldwell.
There you go. Top of people's lists.
Shackleton crater on the moon. But
Just gonna keep naming. This episode is
Venus.
just Josh naming.
Olympus Mons.
while the naked eye astronomers named stars, so we have Algol, Spica, Aldebaran,
The sun,
Rigel,
Beetlejuice.
Betelgeuse.
Beetlejuice.
There it is. Astrophysicists, for the most part, in the modern era, have stuck to the boring numbering, lettering.
Boring, but like makes sense.
Encyclopedic style of identifying objects. So your stumper is, should the IAU, the International Astronomical Union, which has bestowed upon itself the right to name planetary type stuff in the solar system, should they give names to astrophysical objects like stars and galaxies and nebula, and or should it stop giving names to asteroids and comets and mountains and valleys on moons and planets?
More names. More names. I don't know who should be doing the names. Someone should, and I don't know that much about the IAU, so I'm like fine with them being the people that do the names.
Okay, so
someone should do the names.
So like NGC 4673, you're like, let's have that be the Audrey Martin Galaxy.
Yes.
Sure.
Right.
Yeah, totally.
I mean, we planetary people get asteroids and comets and stuff. I like the astrophysicists have some stuff.
Yeah.
Their stuff is hard to get to.
Yeah.
So.
Reverse it all. No names.
No names. So you're
0 names.
There's also
in fact, not even NGC. Let's go with an even simpler thing. 1 through whatever.
That's not practical.
That's
James.
terrible.
Oh, it's freaking practical.
So you want
not 1 through, but
you want a single
1, 2, 3.
single numbering cataloging system for all objects.
Yeah. Well, like Galaxy G1, 2, 3, 4. I don't know.
But like a whole brand new system, start from scratch, and do it logically
whole new system
from the beginning.
Yeah,
because like NGC is new general catalog, or something like that.
Right.
And then some objects are Messier, and some of them have both designations.
Yeah. It's too messy.
SAO.
Why is it too messy? Why does it matter?
It matters because I don't like messes.
But like. But like a lot of things like comets and asteroids, they have catalog numbers also, right?
Yes.
And they're based on like what thing discovered them or how they're discovered. Like I think it's all fine.
And
it doesn't matter.
So you want stars to have names or not?
Yeah, there is that stupid International Star Registry that you can pay to have a star named after you. That's not a real thing,
right? So people could send me money and I'll tell them a star is named after them too.
Yeah,
if they want.
Yeah, same.
Here on Walkabout, send us.
I get asked about that, and I say it's not real, but then
Walkabout.
neither is the IAU thing. It's very arbitrary.
Yeah, but people
you get a cool certificate
you know.
that says there's a star somewhere, and you get a star chart that shows you where your star is. That's named after you. But probably everybody gets the same star chart. I don't know.
Well, what the IAU, it doesn't mean anything, according to What does mean something?
Nothing means anything. I don't know.
Planetary
That's the nihilistic astronomy podcast.
Right. No,
but we give it like the reverence.
But the IAU,
and we trust it, or we,
The IAU is an international body, and by convention, all the objects are referred to by those things, just as they're referred to by NGC whatever, or stars have like some are in this. Smithsonian Astrophysical Observatory or something, SAO numbers, and there's the Henry Draper catalogs. There's HC number. People refer to them. They use those. So they mean something because they're used, right?
Yes. And there's fun themes too, like with the Uranian satellites are all from Shakespeare and other examples.
So you could
Trojan asteroids all come from the Iliad.
It made more sense when there were a smaller number of things known. Like if you try to do it for astrophysics, like the number of
it's too many
quasars known. I mean, this.
So we're not going to name all the asteroids either.
Discovery? Is that what I'm hearing?
Yeah. No, I'm not against discovery. I love discovering things, and I do want something named after me.
Okay, but not anybody else. But Addie, I don't know if we ever got your name.
If I can't have it, nobody can.
Jim
Damn it!
Cooney too. Jim Cooney.
That's right.
You guys done over there?
Yeah, we're done.
What?
I said I like naming things.
You like naming things.
Excellent. All
right. Well, there it is.
I say put Addie in charge.
Today we'll talk about the history of Saturn's rings, matter versus antimatter. But first, this episode of Walkabout the Galaxy is brought to you by the Roche limit. The kids need to get to school, the car's in the shop, and the plumber won't call you back. If you've reached your limit, get the Roche limit. Determining where gravitational accretion can occur around planets for billions of years, the Roche limit is an elegantly simple approach to help you set boundaries. Use the Roche limit to keep all the pieces of your life from getting pulled apart by tidal forces and get back in control. The Roche limit. Keep climbing.
Keep climbing.
American Airlines.
Oh, I like it.
North Face.
Oh, I like it. I wanted to go with something completely different. Keep climbing. I'm done. I'm out of time. I ran out of time. Ooh, Jeep's good.
No, Otter's on the right track. Delta. Actually,
Okay.
Delta's last three slogans all were equally appropriate for the
applicable?
Roche limit. One was like, keeps going around, and another one was like on top of the world or something like that.
Keeps going around.
I don't know, something about circles around. It's like, okay, the Roche limit's
Something
a
about
sphere.
circles.
And another one was on top of the world, which the Roche limit is above the world, right?
Yeah, okay.
Yeah. Space news. So the Axiom 2 mission, which we talked about last episode, did take off, and those folks are up at the space station.
Yeah.
I'm going to maybe piss some people off here.
Oh.
Do it. Controversy.
Well, there's this whole thing about what do you call that mission as generically, because it's not a cargo mission.
It's a private
It's
crew
got
mission.
people in it,
mission.
and we call it now crewed, but they're not. Technically, there's a commander and a pilot, but that thing launches and docks to the space station completely autonomously all the time. And on the Artemis 2 mission, for example, the next one, there's going to be 4
a lot of people just
astronauts
call it
on
a private astronaut mission.
Okay. It's a little bit of a mouthful.
Private astronaut mission?
Yeah.
What would you want to call it?
I'm
Press for
proposing
What's your
mission?
proposal?
blobbed.
No, you're not.
Blobbed mission.
Jim Cooney one.
Because there's four blobs in there.
No, you're not.
Press.
I mean, it's a human. It's a tourist mission.
Yeah.
It's
What do we call
private-
airplane flights? Like, because that's what they're passengers.
They're passengers.
Right.
Yeah.
So,
Passenger mission.
yeah.
People.
Well, your problem is the word crude, because crude,
Because they're not.
because cruise
crew
means
implies
like
you're
yeah.
flying it.
You're flying
right. It implies you're the literal pilot, that you're maneuvering the spacecraft, and maybe they're going to have them press some buttons or something, but they really don't need
They
to.
don't need to, right?
They just have like a panel in the back that's like
the-
fun buttons that light up that don't actually do anything at all.
Yeah,
It's like
one of
when
those,
you go.
like the set of Star Trek.
Yeah.
steering wheels that you
Yeah.
get to your baby in the
Well,
car.
when you go to like Star Wars at Disney World and you do the Millennium Falcon, you've got some levers there and some buttons to
Ooh,
press.
that definitely
right?
works. And
But if you don't do anything, you still get the same ride, right?
Right.
Good
So it's
to
kind of
know.
like that.
Good to
you know.
know.
you do, but the person next to you doesn't. You're
Yeah.
controlling somebody else's seat.
Oh,
Dun dun dun.
Just kidding. You can't go to that hotel anymore soon.
I know. Yeah.
The
Star Wars hotel is
There's
closed.
a
Star Wars
Star Wars
Hotel
hotel.
was
Yeah, it's like a cruise.
closing down at the end of September.
Yeah. What else launched? Lots of stuff is launched.
Lots of stuff is launched, and previously, of course, JWST launched. I think there's lots of JWST.
But there's other
Cool.
space news
Oh
stuff.
yeah, the Spitzer Space Telescope, which went offline, I don't know how many years ago.
2013?
No, it was more recent than that. It was
It was an infrared space telescope.
yes, and it had a cooling element to it that ran out probably in
Long
like
time ago.
20, I don't know.
Yeah.
But I thought it went offline more recently than 2013.
Oh, 2020.
Yeah. But a new, I don't know what it is, a new company in tandem with the U.S. Space Force, I think, they're going to try to start it up again.
What are they going to do with it?
They're like going to drive up there and jumpstart it or something. What do you mean by went offline and start it up?
So, yeah, I mean, it's this like private company called
Yeah, but what are they going
Rhea.
to do?
Well, I don't know.
Oh, well, you started talking about it.
They are making plans now to go to Spitzer instead of making their own new infrared telescope.
But this is what I'm asking. Literally go to it?
Yes, literally go to it. Like how Hubble was serviced. They want to go service it.
Hubble was serviced by blobs.
By humans.
by
This is
human
going to be
blobs.
serviced by people?
I don't know. That'd be pretty cool though.
probably-
it's very far away.
So, like, so they had to shut it down because it could no longer do the cooled part of its mission for like a long time, but it was
Yeah.
still taking data. So like it probably ran out of like fuel to stabilize its orbit or something too, right?
I think so.
So you could send a robotic spacecraft to it. I'm
Where is this
hypothesizing
orbit?
right now. You could send a robotic spacecraft to it and help it like stabilize itself.
Yeah.
I don't know.
Well, yeah.
I think it's trailing Earth in Earth's orbit, but it's
So we don't have the means to send
pretty far
people
away.
to something like that at the moment.
no. But I don't know. Rhea might. No,
No,
probably
they
not.
don't. They definitely don't.
It's an Earth trailing orbit, which was the same one later used by Kepler.
So they would send maybe perhaps a robotic servicing mission?
Perhaps. Yeah.
Are they going to put more
We're
coolant?
just making stuff up?
Because it was like
Because the coolant is the key thing.
that's the key
right?
thing. Like it was an okay thing. I mean, it did stuff even when it ran out of coolant, but it was kind of crappy. Like
I mean, it's not the biggest
that would
telescope.
be awesome.
Right. So
I would
Yeah.
be very happy about that.
recool it.
the
More ice cubes.
the benefit of the
Resurrection mission.
telescope is that it's in space, so it doesn't have to deal with the atmosphere, and you can look in the infrared. But to do that, you need to have a cool detector, and the coolant boils off eventually.
Yeah.
It
Or-
includes a servicing spacecraft to travel to the telescope.
Oh, thank you.
Huh. Somebody's actually looking into the topic that we're talking about.
Wow.
Curious concept.
Wow.
But it doesn't say anything if they would try to use coolant again or not.
Yeah. Okay.
But it's interesting. It's an interesting jumping off of like. So we've started doing these ISAM. I think is the acronym in space service assembly in manufacturing.
Oh.
So like where you send robotic spacecraft to like service and or assemble spacecraft. And we've
Okay.
done it in orbit a few times now. So there's been a few test missions where
Okay.
companies have sent another mission up and it robotically docked with a different spacecraft that's already up there and like boosted its orbit.
Right,
Or most of them so far have just like demonstrated you can dock and do a thing.
You can go find another satellite and
and
connect
dock
yourself
with
to it.
So a couple of companies have done this so far. And obviously there's a lot of interest in that from companies, but also defense, military satellites, things like that. And so but that's always been in low Earth orbit. So
Yeah,
this would
I
be a
mean-
much more complex one. And it is for allowing it to continue to do characterizing potentially hazardous near-Earth objects. So it could probably still operate in warm mode and look for
think
asteroids.
So. Yeah, you can do identification in warm mode.
But it's kind of incredible that they can do anything at all because the spacecraft was not designed
To do that.
to have anybody come
Right,
robotic
yeah.
or otherwise
Yeah.
to come
Yeah.
connect to it, right? So we say docking, that implies there's something there that you can grab onto and do something with. So, well, that's interesting. Yeah.
News to me.
The
Thank
other
you. That's news
much,
to our listeners too, hopefully.
Yeah.
much larger infrared telescope, of course, that's operational,
JWST.
WST.
It keeps doing its thing.
So it's done some planetary stuff,
Yeah.
planetary observations.
Yeah, there was a cool study that just came out about a main belt comet. Some people observed an active main belt
So
comet.
what is a main belt comet?
Yeah. So it's just a comet that's in the main belt. It's exactly
In the
what it sounds
asteroid
like.
belt.
Yes, in the main asteroid belt.
Right.
This
Why?
kind of gets
How'd it
at
get
one
there?
of my
Orbital
sneaky things.
dynamics.
Well, not necessarily. Because there's a
Maybe it just lives
continuum
there?
between like asteroids and comets, and you think of like asteroids as being like rocky and having more circular orbits, and comets as being more icy and having like more eccentric
Right.
orbits. But there are asteroids that have very like elongated orbits, and there's comets with very circular orbits that are like all over the place.
But they should be in there, right?
Well, that's the
What do you
cool
mean
thing
it
about
be or
in
shouldn't
They
there?
shouldn't be in there because
it
comets
should've,
shouldn't
like,
form inside the frost line, yeah?
Right.
yeah. There was a lot of like reorganization of the solar system pretty early on.
And the frost line or snow
Has
line or ice
moved
line
over
moved.
time.
Yeah.
So anyway, this
Yeah.
is an object in the main belt of asteroids,
correct.
which is between Mars and Jupiter.
That's correct.
That otherwise its orbit looks like an asteroid, but its composition looks like a comet.
And
this is what you're saying?
Yeah, and it's active. So they took some spectra of it while it was sublimating away volatiles.
Okay.
And it's sublimating away water ice, which is really cool and has implications for all of the potential like water ice that's just buried in the main asteroid belt.
Sublimating away volatiles is your way of saying defrosted.
Sure, yeah.
Yeah. So the ice was
Just my way. No one else says it that way.
Yeah, there's also some cool, speaking of ice and water, there's some new images of Enceladus that have been released.
One of
Although
my
I haven't
favorite
actually
places.
seen the images. I've just seen articles that say there's new data.
It's the hearsay astronomy podcast.
Yeah. So that's okay. Let me rephrase that. I have actually seen these images, but they were not publicly released. I have not seen them in the publicly released articles I've read about it.
Ah, okay.
So I do actually know that these are true articles.
The articles are true.
Yes.
And what do they say?
So they imaged the plume, the jet coming off of Enceladus from the South Polar region to see like, okay, how big is it? Blah, blah, blah. And it's huge.
How
it's
big?
like many, it's
Yeah,
like
it is.
tens of Enceladus radii.
What?
It's like really
How
huge.
is
What
that
are
even
they-
possible?
JWST has a much bigger field of view than like Cassini was able to get because obviously different location and all of that. And so they can see that it's like really, really extended. And I'm trying to look at the number right now. But
Interesting. Okay.
New telescopes wider and higher sensitivity showed that the jets of vapor shoot much farther into space than previously realized.
Well,
Many Enceladus diameters.
I guess that's not surprising, right? I mean, once its
Well, we know that-
escape velocity, then it's
Right.
just going to keep going.
Yeah, but if at densities that are like high enough that you can detect,
That's great. Yeah.
like that's pretty impressive.
That's pretty
right?
impressive, yeah.
Like,
That
not
made it-
just you have like three molecules
Does it-
that are still a million miles away.
Does that imply more volume spitting out than we had previously thought?
It either implies more volume or like higher speeds or something. Yeah, I don't know.
Interesting. So Enceladus has these famous fissures at the South Pole with
Yes, the
geysers
tiger stripes.
spewing
Are there ever any
water
geysers?
vapor out there. Sorry?
Ever any Gausers?
Gausers. Excellent question.
Thank you.
So there's a subsurface ocean at Enceladus, and as far as we know, like from the Cassini measurements, this is like a continuously active process. And the best models for what's enabling there to be liquid water beneath the surface require it to have always been liquid. And I think we talked before about like when we were talking about the Uranus moons recently and their subsurface oceans. It's like easier to maintain things in the water state than to get them there.
Right.
And so that the same holds true for Enceladus. And so then people do the calculation, okay, how much stuff is coming out of the geysers? Our instrument on Cassini actually measured that. And you extrapolate it back 4.5 billion years. So what fraction, bonus advanced spur of the moment trivia, what fraction of Enceladus's mass do you think has been lost
I've done
to
this
the
calculation.
geysers if they have been going at their current rate for 4.5 billion years?
Oh my god.
It's something like
10%.
3%. I feel like it's not correct.
Oh, 30.
It's 10%.
Nice.
Yeah.
Too bad that one didn't count. Oh.
Yeah. No points.
No cash.
That was just the warm up. It's the audition round. So anyway, it's kind of cool. So it means it could have been going for the whole history of the solar system.
Wow.
It means that the moon is maybe now 10%-ish. I mean, these, we don't have this nailed down super precise, but it could be about 10% less massive. Anyway,
So it's exciting. They also have spectra of it because it's JWST, so they can identify like different molecules and stuff like that. And I don't think they've said anything about that in the press releases.
It's going to be mostly water.
Yeah, but there is some other interesting stuff, I think.
Probably.
There's been some papers recently that have talked
Fish?
about like there's probably methane.
Yeah.
Maybe some
ammonia,
some fish.
fish.
Some eels,
Yeah.
maybe some what are those called?
Swordfish?
Swordfish. That's why there's those fractures.
I see. right? The swordfish are sawing their way out from the subterranean ocean and launching themselves into space around Saturn.
Yep.
That's good science. That's just good science.
That's just good science.
Just good science.
Let's see, what else?
Yeah.
Sharks.
There was some other space
other
newsy
space
thing I wanted
news.
to talk about, but I don't remember what it is now. So
The Japanese.
oh
mission
yeah,
to the moon.
just yesterday I believe LROC, the Lunar Reconiassance Orbiter Camera, released images of the landing site. I'm going to generously say of the iSpace, which was the Japanese private company lander on the moon.
And it did end up on the moon,
It is on the lunar surface,
but not operational.
but not operational, and probably not all in one piece.
It sounds like it ran out of fuel kind of just a little bit too soon or something.
It's like they were so close. I think they were like meters or tens of meters above the surface.
Yeah.
But like that final touchdown, you have to slow down enough.
Yeah.
And I think they didn't slow down quite enough or something.
Oh.
It didn't like it's hard to tell. It was a pretty small lander, and the image they've released so far, you can like tell that there's something there that's different, but it's really hard to tell. From what I've seen, it's really hard to tell. Like, it doesn't look like there's giant debris everywhere, but there's
Is
clearly
that the one that spread the water bears all over the place?
No, that was a
Oh,
while ago.
different
This was the one that like just happened.
Oh, okay.
Yeah.
Okay. Sorry.
It's okay. There's a lot of them now, but none of them have been successful.
Right.
Yeah.
Except the Chinese had a successful one,
Right.
and there's gonna be another successful one coming up this year,
Oh.
hopefully very soon, like
Is that
this
a
summer.
secret?
No. Astrobotic is supposed to launch it like soon.
Oh,
Is that the one that's going on the first flight of the Vulcan rocket?
I think no.
So, okay, I thought, yeah. Well, we have our couple of astronomy main stories
Oh,
to talk about
interesting. Cool.
too. Shall we get to those?
Yeah.
Sure. Well, one of them, since we won't spend too much time on it, is about
Yes,
Saturn's
it is
rings.
waiting on ULA
Okay.
and Vulcan. So that could actually be problematic because they recently had an
They had a little
engine
bit
thing
of a
they had to
slip.
check out.
Right, but sometime this year in 2023, this is the new rocket from United Launch Alliance, which has got
We're back on space news. Sorry, everybody.
engines from Blue Origin as on the main stage, and their first payload will include a lander to the moon. Yeah.
By Astrobotic. It's called the
Right.
Peregrine Lander.
Great. So we'll keep an eye out for that and
And there's
update
supposed to be another one later this year by a different company.
you. So for Saturn's rings, which we've talked about many times on the podcast, there's been
Really?
this big open question about how were they formed and how long have they been there and how long are they going to last?
Yeah.
And the conventional wisdom a few decades ago was they formed when the planet formed, and they're still going to be there when the sun it dies.
Sure.
Billions.
And part of
years
that
from
is
now.
like, as scientists and astronomer people, we like to think that we're not looking at anything at a special time.
Exactly.
That as we're observing things are how they've always been, because that's a lot easier. Well, sometimes it's
Also,
a lot
it's more
easier.
likely.
It's more likely, right? Just because like space is
Yeah.
old.
Yeah.
The idea that you happen to be looking at something when
At a
it's
special
is a special
time.
time is silly.
Right.
Except that we see like novae and we see supernovae.
Things happen.
Sometimes it's
Things
special.
happen.
Right. So it's a
So
question
sometimes
of
there
like,
are special things.
are you looking at a system that is largely static and unchanging, or are you looking at a system that is dynamic and changing dramatically? And if it's a dynamic system, anytime you look at it, it's going to be different than any other time. So every
so
time
hard.
will be special,
Yeah.
right?
And as
so
we discussed last time,
it's like if you
we
drop.
know the solar system is chaotic.
That's right. It's
Wow,
like if you
bring
drop
it
in,
back.
if you drop in to watch a play, what are the odds that it would be right when they're singing that song? Well, very low.
Pretty high.
But anytime you drop in, there's going to be some song they're singing.
Oh, that's true. Unless you know the play and you know when you're dropping in.
Yeah. You have
So-
like memorized.
Yeah.
Cassini made measurements of the rings that indicated first that they're not very massive, which means that it's easier for them to erode and easier to darken them by hitting them with micrometeoroids.
These are the main rings we're talking about?
Yes.
Okay.
So the rings that you see if you look at Saturn through a telescope or binoculars even.
If you're watching us on
Or-
the podcast, on the video, the rings that are always prominently displayed behind Josh
as a squiggly line.
as a squiggly line.
Yeah. So the main rings have the mass that's about half the mass of what is referred to sometimes as the Death Star moon around Saturn. Mimas.
Mimas. Mimas?
Mimas.
Mimas.
And I say Mimas. So that's as these things go, it's not a huge amount of mass. It's a little bit tricky, though, to come up with an explanation for how you break up that much material and put it into orbit around Saturn much after the age of the solar system. So that's always been, in addition to the, like, what are the odds argument, another argument has been, like, well, how did you end up breaking up that much stuff and putting into orbit around Saturn, say, 100 million years ago? 4.5 billion years ago, it's easy. You got all this stuff orbiting the planet because you're in the early days of the solar system. You're forming the planet. All the stuff is flowing into the planet. So that's your leftovers. So that's been a little bit of a tricky thing. So the arguments for, like, the rings are young, one of them is that they can be darkened by meteoroids hitting them. They're very bright. They look very icy.
Yeah, they're not darkened.
And they're not very darkened.
How,
so,
like, what's the albedo?
Bright.
high.
Okay.
Yeah.
Big number.
Sweet. Thank
More,
you.
Something
more
close
towards
to
the
one.
1 instead of towards the 0.
Okay.
And like,
yeah,
I mean,
more
like
than
actually
50%
high,
is
right?
like
It's
super
like-
high.
It really,
They're like watery.
the
They're like
surface,
water.
the surface composition looks like 99% water ice.
That freaks me out.
So
Go on.
So that's one argument.
Water ice?
Water's really scary.
There's some new
He's an alien
papers.
from Signs.
There are some new papers out that are arguing from another line that the rings are young, which is something called ballistic transport.
Ooh, I love me some ballistic transport.
Like they're just shooting at each other?
That's some easy physics. I like that.
You do?
Yeah.
So ballistic transport in the rings is actually kind of complicated.
Oh. Because rings.
Yeah, because there's this third body.
It's pretty
right?
easy if we're just doing it like in our impact experiments
That's right.
and on the moon.
Yep.
It's really pretty straightforward.
Yeah,
Sorry.
and physics
Saturn
1.
should just do that.
You know.
Pretty stupid.
So in the context of the rings, meteoroids come in, they hit ring particles, stuff blasts off the ring particles and lands somewhere else. It gets transported ballistically to some other part in the rings. That not only transports material, it transports
Ideas?
Angular momentum.
angular momentum. And that means that you're exerting a torque on the system, which causes the system to evolve dynamically.
I love it when Saturn
So
torques.
it's not just a redistribution of material, it's a global moving around of broadening,
For the
spreading of
listeners,
ring
Josh
system.
is doing a lot of
Gesticulating.
gesticulations.
And so that gives you another time scale, which is also basically saying rings are like 100 million years old.
Yeah. And we'll be
Weren't
gone
there-
in another 100 million.
And also
Yeah, so they're 100 million years old, but where is that in their lifetime?
looks like middle age.
Everything's
Ish.
always middle aged. The sun's middle aged. The rings are middle aged.
True.
Boring.
Yeah.
I'm not middle
So
aged.
it's interesting. I think that the last word on the age of Saturn's rings has not been written, although there were 3 papers that came out this month on this
Oh wow. Hot
that are
topic.
basically saying
Jeez.
this is it. We've solved the problem. The rings are young. They're like 100 million years old. They probably only got another few 100 million years to go or something, because Cassini also measured like the rate of material going into the planet.
That was one of the things it did in its final dive.
Yes. Yeah.
R.I.P.
So, but I think there's still a lot of unknowns. We don't really know that the mass flux into the rings that we're observing now has been continuous at that level and that kind of thing. We also don't still really have a really good model for how they formed. Did they all form
like
in
if there's
one
more
event?
sources.
Yeah.
Yeah.
So
It's complicated.
that's interesting.
Because the E-ring has a source.
The E-ring has a source.
Enceladus.
And it's been there.
Plume.
And if that's been going for
really?
4.5 billion years, that's going to keep going.
I feel like I should have known that.
Yeah.
But I don't.
But now you do.
No, I do.
Before we transition to our astrophysical cosmological
Cosmo.
topic, our trivia is ring and Roche limit related.
Great.
When were the planetary rings in our solar system discovered?
No one knows.
That's a bold assertion. So for Jupiter, Saturn, Uranus, and Neptune, we'll leave the little, qual
like we have to name for each one.
For each one, I want when the rings for Jupiter were discovered, when the rings of Saturn were discovered, when the rings of Uranus were discovered, and when the rings of Neptune were discovered.
That's a good question. I like it.
Thank you. Easily explained.
Yeah. Yeah.
Not one of my lengthier trivia, rambling.
Is there going to be follow-up later?
Nope.
Oh.
That's it.
That's it. 4 parts.
I don't understand. What do I do with
4
myself?
numbers.
I usually spend this time thinking about other things instead of listening to you.
Well, now we are going to go to other things.
Oh, but I have to pay attention.
Well, you can listen to Jim instead of me.
Great.
You can ignore me. That's no problem.
Check.
Most people do. Most of the time.
Coffee.
Yeah, most of my classes do. Most of the time.
Bring it, as Sam Buttrey would say.
Potentially, albedo was an answer on Jeopardy. Or
That's
a
what I
question
heard. I haven't seen
yesterday.
that episode.
Shh. It's not spoilers.
Potentially.
Anyway, potentially big news in the cosmology community.
What is it?
This result. So there is a symmetry that we always thought was just
There's a space symmetry or asymmetry, one word.
a space symmetry. Symmetry is beautiful. We love symmetry. Everybody likes a symmetric face is very pretty, et cetera, et cetera. But symmetry,
It has to be slightly asymmetric.
okay,
Just like the universe.
just like the universe. Oh man,
Maybe that's
Beautiful.
why we find a slightly asymmetric
Yeah.
face beautiful.
We are the
because
universe that
primordially, genetically, we know that the
need
universe
a
is
tiny bit of
was slightly
asymmetry.
asymmetric between matter and antimatter.
love it.
Yeah. So this story isn't mostly about that matter antimatter symmetry, but it's related to it.
Okay.
We have that very slight asymmetry where at the beginning of the universe there was just a little bit more matter than antimatter, which is why we're all matter now, because it all annihilated except a little bit of antimatter that was left over.
A
little bit left over, which is weird, and we're trying to understand why that asymmetry happened. And one way of kind of attacking that is looking at a different kind of symmetry in the universe, which is parity, which is mirror symmetry, basically. So that is like, are the laws of physics the same if you look at them mirror reversed?
Okay, it doesn't mean
don't
that
get it.
there's as many
Right-handed
left-handed
versus
things.
left-handed, right? So
Oh.
yeah.
What are we reversing?
Well, mirror reversing space. Like your right hand and your left hand are not actually mirror images of each other, right? If you took
Right thumb's a little weird.
because they're 3-dimensional. But if you took yeah. So the question has always been like, is the universe itself kind of parity? Meaning, is there a symmetry in the universe? Is there more left-handed stuff or right-handed stuff in the universe, for example? What does that even mean? How do you define left and right-handed?
Well, wait a minute. So
Okay. I'll wait.
at first I thought I knew what you were talking about. Then I thought I didn't know what
I
you were talking
transitioned.
about. Then you came back to what I
Oh,
originally
it's like
thought.
a regular colloquium.
So if you take a tracing of a right hand,
Yes.
you can tell that that's a right hand because a mirror image of it.
No, a tracing of a right hand is
Would be
parity. That is,
symmetric.
if you mirror reverse that, you'd say that's the left hand, and you'd be fine.
Right. Okay, because it's just the outline.
Right.
Yeah.
But if you took a 3-dimensional right hand and mirror reversed it, it's not the same as a left hand because the palm and the back of your hand would be reversed
Right.
and wrong.
Okay. So what do you mean when you're talking about parity in this?
So the question is like, are there the same number of right and left hands out there in the universe, kind of a thing?
Okay. So like so
galaxies that spin one way and galaxies that spin the other way.
Right. Sure.
Okay.
For
Really?
example. So the question is, are there? I mean, there should be, right? It seems like there should be, but maybe there isn't. Maybe there isn't.
for molecules, there
Going
are
back to a hand.
molecules can be left-handed or right-handed.
Right.
So are you saying, is the discussion about whether there are equal numbers of left-handed and right-handed molecules?
In this case, it's a discussion of is the distribution of galaxies have a parity associated with it. So that is, you can take galaxies. So say you have 4 galaxies. You can draw. So it's because the simplest, like we just said with the hand thing, with 2-dimensional things, they're always reversible, and that's whatever. You need a 3-dimensional thing to test whether you have mirror symmetry or not. So the simplest 3-dimensional shape that you can make is a tetrahedron, right? You can take 4 vertices and connect them, and it's kind of like a pyramid, but not necessarily
with 3 sides instead of 4.
Right. So it has
And a
3
bottom.
sides and
bottom.
and 4 vertices, right? And what you can do is you take galaxies and you take, say you have a catalog where we've mapped out the positions and whatever of a million galaxies. You take each galaxy and connect it to each other galaxy, make a tetrahedron out of every combination of 4 galaxies that you can.
Okay.
And you define some kind of right and left-handedness to that.
How do you
And
define
the way
that?
the way they do that is basically like you take one galaxy and then you have the 3 other galaxies, and if like the distance between those galaxies increases as you go one way around, you call that left-handed, and if it increases the other way you go around, you call that right-handed. Okay. This is a little bit hard to see what I'm saying if you're listening, which is what most of our listeners are doing.
It's hard for me to see what you're saying, and I'm looking.
Right.
Okay, so all right, let's take that.
So basically,
the
they're
3
looking...
galaxies. I can go clockwise or counterclockwise. If the second 2 are further apart than the first 2, that would be left-handed. And if,
for example, yeah,
second 2 are closer together than the first 2, that would be right-handed.
Right, exactly. You just right. And so the question, and if the universe is like totally symmetric, then you should expect to see the same number of one kind as the other kind, right?
Okay.
And they did that,
and
they're not the same. So to 7 sigma confidence, they're claiming that there is not parity in the universe.
So
there's not mirror symmetry. There's a certain handedness to the universe,
and
which
now we're talking about like distribution of stuff.
Distribution of stuff in the universe, which could come about if there was a tiny lack of symmetry in the universe in the very early universe that will imprint itself on the structure of the universe much later on. And that tiny bit of asymmetry in the early universe could be associated with the tiny bit of asymmetry that also gave us the matter over the antimatter.
Let me ask this question. Well, go ahead.
Well, so like we know that the universe itself isn't symmetric, right? Like we know that like things are distributed strangely, and we get filaments and we get weird things, and like overall the distribution is not perfectly symmetric.
It's not perfect, but on
homogeneous.
Well, right, but on the largest scales, it is.
Okay, and like so, I'm reading a little bit of the article now because I definitely didn't do that before, but I am doing it now. But like it's like there's symmetry in the electromagnetic and strong interactions. Those those have parity even. So like those are the same mirrored, but the weak force is not the same mirrored. And
that's right. And that's the kind of the connection between the microscopic the matter antimatter thing and this big thing is the universe. Yeah, back in the 50s or whatever, discovered that the weak force does not obey parity. That is, it's not this. The universe is left-handed, and
you're just saying that because
I'm left-handed. That's right. I discovered, by the way, that the word right-handed is like from that. It's like correct, right? It's the way it should be.
Yes.
And that the left is wrong.
Really? Yeah.
I didn't know that.
Which is
it's called
minorly
gauche
offensive
in French.
To us lefties. Right. But in any event, the universe.
Righties don't care.
Yeah, I know you don't.
No, I don't.
The universe is left-handed, a little bit.
So
ever so slightly.
Okay,
so maybe it's not surprising that little bit of quantum mechanical asymmetry business in the early universe caused a big asymmetry in the universe now.
So, all right.
This is complicated.
It is.
It is complicated, but if it's true...
Yeah, give us the big picture.
If it's true, then this could be the mechanism which caused or I won't say the mechanism, but this could be related to why we have more matter than antimatter. And so this is part of the explanation for that, which is a mystery that has been plaguing us for a long time. We have talked about it on the podcast before. And if so, this is I've heard other cosmologists say now, they're still like, it could be that they did something wrong in their analysis. This is very complicated.
But are you saying that it's coming from the asymmetry of the weak force, or are you just saying, that's just another one of this list of asymmetries?
It could be coming from the asymmetry of the weak force. Because
how does a force have an asymmetry? I'm sorry. Because is that something you can answer in words I can understand in 30 seconds?
Probably not. I mean, so the weak force is responsible for things like radioactive decay, and so you get particles that are thrown off of radioactive decay things, and they are preferentially one way rather than another way.
Yeah.
All right, I'll take that.
That's not a great explanation.
I'll take that as your 30-second explanation.
Yeah.
That was only 10 seconds.
So it's sort of in that family of things or whatever. Somehow that ends up with this weird asymmetry in the distribution of galaxies. But earlier, the question I was going to ask is, what are the odds that you would get a perfectly symmetric? Like, isn't it sort of incredible to imagine that there wouldn't be an asymmetry?
No,
like, if I just take, like Addie was saying, there's filaments and things like that. It's like, it's not pudding, it's spaghetti.
It is, but if you...
And so there's always going to be, and when you add it all up, you're not going to get 0.
No, you're not. But this is like flipping 10 trillion coins, right? The chances of getting anything but when you flip 10 trillion coins, you're going to have 2 or 3 off, right?
Right.
But the chances of having anything more than that off, and here we're saying it's very significantly different from
50-50.
50-50.
Okay, it's not just that it's different. It's
7
different
sigma.
by more
Different but it's
what?
different.
Random
Right.
numbers.
This
Random noise,
7 sigma thing means that you by random chance, it's different from what you'd get by random chance with a huge amount of statistical
Yeah,
significance.
they did some sort of insane number of simulations for this and looked at like a quadrillion.
Well, not
simulations
I mean, they
of,
were
like,
looking
a
at
lot of galaxies.
right
Also.
because you have to make a tetrahedron
Yeah, they did
out of
tetrahedron.
every combination of 4 galaxies in a 1 million galaxy volume of space, and that is a lot. It's a trillion combinations or something like that of
Right, so they can't actually do that.
They did a lot of math.
yeah.
And a lot
Well,
of
so they did. So
They
did some
sampling of it.
They did some trick. Well, yeah. So there's it's complicated mathematically enough that maybe they made a mistake, and that's why this isn't like they haven't won the Nobel Prize yet. But some cosmologists I've heard from this say that if it's true, if they really do, that it's borderline Nobel Prize stuff because it's very. It's very significant to explain why there's more matter than antimatter in the
7
universe.
sigma significant.
That's cool. All right. Well, closer to home then.
Well, this is pretty close to home. One of the authors is at UF.
Okay.
That's right. 2 of the authors, I think, are at the University of Florida, just up the road from us in Gainesville.
When were the rings of Jupiter discovered?
Jupiter, long time ago, probably telescope.
No, someone went there.
I just mean not naked eye. So Galileo ish. When was he? I'm always bad at dates.
1912.
You're saying 1912?
1912?
1912.
1850.
1850, and you're saying 1600s?
Yeah, I'm saying
Galileo.
like 16.
Let me ask you this, Addie.
Uh-oh.
Oh, boy. That does not sound like you're
Have
right.
you looked at Jupiter through a telescope?
Yes.
Did you notice any rings?
Yes. Oh, Jupiter! I was thinking of Saturn.
Okay, I'm glad I
Jupiter.
asked you.
Good clarification there.
Yes.
Sure. Let's go 1873.
Okay. 1979.
Whoa!
Yeah. By
That was before all of us were born. I was being generous. I'm saying that as a statement.
Voyager 1.
You just gave yourself away.
I was gonna say Voyager 1.
Really?
I should have gone.
Yeah.
But then,
it's
then
a
you were
backlit?
talking about so early that I was like, maybe I'm
I
really
saw it
wrong.
in the backlit.
It's
Yeah,
That's so
I forgot
cool.
about that.
Jupiter's ring is very, very faint
It is.
because it's just a tenuous dust ring. And just like you can only see the dust, hopefully, in the movie theater when you look back towards the projector,
Yeah.
Right.
you can only see the dust in Jupiter's rings easily when you look back towards the sun. So you have to go past Jupiter
Yeah.
to take those images. So 1979, Voyager 1. Okay, now for Saturn.
Okay, so I'm gonna go with like 1633.
I was just gonna say Galileo.
Yeah.
He's the one that discovered
Is that close enough?
Yeah.
that I'm aware of.
This is the
Is that
gimme
when-
question.
Is that when Galileo
Yeah.
was alive?
Yes.
Anyway, this is Galileo, and I don't want Audrey to embarrass herself any further, so we'll just go ahead.
Wow, thank you so much.
1942, Galileo.
2012?
1610.
Oh, I was a little late.
1655 is when it was recognized that that was a disk around the planet instead of some
just like ears.
moons or something like that. So Galileo didn't really know what he was looking at.
cinnamon buns.
Yeah.
Yeah.
All right. How about Uranus?
How about Uranus? So Uranus also probably was Voyager because it was probably backlit, or was
I
it
think
later
Uranus,
than that?
You need like infrared telescope.
Oh, there was. We've done it with Hubble.
1983.
83,
What was the answer for Jupiter?
79.
I don't know why I said 83. I don't know what went up in 83, but 1992. I changed my name.
You're changing your answer to
81.
92? 81.
82.
1977
Earlier.
by
Closest.
stellar occultations from the Kuiper Airborne Observatory. Yeah.
Kuiper Airborne Observatory was flying that long? Wow. I didn't
Yeah.
realize that one was so early.
KAO. Finally, Neptune.
1987.
1978 in between those two.
I'll go with 82 again.
You're going to win this one, Audrey. 1984.
Oh, that's a good year.
Also discovered by stellar occultation from the Earth.
Cool.
But discovered initially as arcs, so we weren't sure what we were looking at. It looked like ring arcs because they weren't seen on both sides of the planet. Then when Voyager 2 flew by in 1989...
That's what I guessed.
Is when it was confirmed that they were rings. So I'll give you also credit
I said 87,
for that.
but that's close. I was thinking.
Yeah. Voyager 2 confirmed them as rings photographically. Cool. Uranus, the rings were known from stellar occultations, but photographically they were first observed also by Voyager 2 in 1986.
Good old Voyager.
Now, of course, we have these amazing pictures of the rings of Uranus from ground-based and JWST.
Yeah.
Which, in my career, it was like, we can't see those unless we send a spacecraft there. It's like, no, sure you can. Just we have these amazing optics and amazing telescopes now.
Yeah.
I want to see.
While it may have felt like being ripped apart by tidal forces, it was just another episode of Walkabout the Galaxy. Give us 5 stars and we'll give you the universe. Be sure to follow us on Facebook and Instagram, but not Moodle, to get all our updates. And check out our website at walkaboutthegalaxy.com. Subscribe to our YouTube channel. Catch up on old episodes wherever you get your podcasts. Follow us on Twitter.
At walk_the_galaxy.
And ask us questions via the ancient technology of email at wtg@ucf.edu. Our theme music was composed by Richard Rusick. Production assistance is provided by Logan Basinger. Thanks to our listeners in the Netherlands and around the world. Stay safe. I'm Josh Caldwell.
I'm Maddie Dove.
I'm Jim Cooney.
And I'm Audrey Martin.
We're the astroquark signing off until the next episode of Walkabout the Galaxy.
Occultations.